Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is hydrocarbon combustion, and the sections in the textbook are 15.1 to 15.2. So here are the learning outcomes. At the end of this, you'll be able to define what is a hydrocarbon. You'll be able to balance a hydrocarbon combustion equation using both theoretical air and excess air. You'll be able to calculate what's called the air-fuel ratio. You'll be able to determine the dew point temperature of combustion products. And you'll also be able to balance an incomplete combustion reaction using an element balance. So first I just want to talk a little bit about how we get hydrocarbons. And the source of almost all hydrocarbons is crude oil, which is a natural source of hydrocarbons. And the thing about crude oil is it's a mixture of all sorts of hydrocarbons, from very small chain to really long chain molecules. And so if we want to separate those out into individual components, that's done via distillation. And so here's a schematic of a distillation column. And what we do is we take crude oil and then we put it into this large column where we have a heat source at the bottom. And what that causes is, as the crude oil comes in, it's going to come down here and begin to boil, and the vapors will go up. And what ends up happening is, as the vapors go up, it will cool down, and we'll get some liquid. And eventually what you'll end up having is a little bit of liquid on each one of these trays. And these trays are essentially perforated discs where some fraction has been drilled out, so maybe like 30 or 40%. And so at each one of these is sort of like a boiling pot of water with holes in the bottom, and so vapor will be coming through and liquid will be dribbling down. What that means is I'm going to have phase equilibrium on each one of these trays, but since I've got a mixture of materials of hydrocarbons, the vapor phase at each tray is going to have more volatiles or smaller chain molecules than the liquid. And then what comes down is the liquid comes down and begins to boil here. And so I end up what's called fractionation. I'm fractionating each time. So I have small chain hydrocarbons up at the top, small, which are the more volatile, like methane, for example. And I have very long chain molecules here at the bottom. So for example, like octane or dodecane or even longer types of materials. And eventually at the end I get things that I might make, for example, asphalt roads or asphalt roofing on, whereas up at the very top we have our liquefied petroleum products like methane, ethane, and propane. So that's sort of the process that's done, and this is in the realm of chemical engineering. Here's a picture of what actually these distillation columns look like. They're sort of interesting. You see they're very, very tall structures. It can be several hundred feet in length. These are stairways so that you can actually access them. There has to be a finite distance in between each one of these trays, which is why they get so hot or so tall. And you see that if you've ever been like boiling some food, for example, you get a lot of bubbles. And so since you've got a lot of foaming going on in here, there needs to be a finite distance between it. So at some point these get a little longer, a little taller than you might want, but the more different types of components you're trying to separate, the taller the column gets. All right, there's just a little bit of background on how we separate out hydrocarbons. Now, what is a hydrocarbon? Well, it's simply a molecule that has both hydrogen and carbon on it. And so what I show here is a very simple hydrocarbon. This right over here is methane. And the chemical symbol for this is CH4. I have one hydrogen. I have one carbon and 4 hydrogens on it. Now, hydrocarbons can have more and more carbons on it. And so the next picture here I show, this is octane, which has 8 carbons on it. 1, 2, 3, 4, 5, 6, 7, 8. And then we have hydrogens single bonded on all of these. Now, some hydrocarbons could be double bonded, but right now we'll look at what are just single bonded hydrocarbons. And so we're going to have 4 bonds on each one of the carbons. Now, the chemical formula of this is going to be C to some number M, H to some number N, and if they're all single bonded, what you can see is that it ends up being however many carbons I have, I'm going to have twice that many hydrogens plus 2, and I see it, I've got 2 hydrogens for each carbon that I have, and then I have these 2 on the end right there. Now what I show here, this is a linear chain hydrocarbon, it's all in one big long line. I could go ahead and have a branched hydrocarbon, so I could take my octane, 1, 2, 3, 4, and I could do maybe 5, 6, 7, 8 carbons like that. And this would be a branched hydrocarbon because it's all in branches. But what I find out is that this formula right over here remains the same, because if I count the number of hydrogens, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So again, I would have C8, 8, H18, whether it's linear or whether it's branched. All right, so here's a listing of the first 9 or 8 hydrocarbons, starting at methane. So methane is CH4. Ethane is C2H6. So again, we have 2 times 2 plus 2, so that gives me that 6. And then moving through as we get to longer and longer chains, propane, butane, pentane, hexane, heptane, and octane down here, C8H18. Octane is the most prominent component in gasoline, for example. So gasoline is a fairly well refined, but not exactly all octane. And so when you go and fill up at the gas station, you'll see an octane rating, which is a measure of how much octane is in there. And then I've skipped a few down here, but I've listed dodecane, which is C12. And this is a pretty common one that you run into as well. Or C16 when you start talking about diesel fuels. You don't need to memorize these names, but there's various mnemonics if you wanted to go ahead and memorize them. So for example, there's one mnemonic I pulled off the web. Monarch Edward prefers birthday parties. Methane, ethane, propane, butane, pentane. His Highness offers no drinks. We've got hexane, heptane, octane. This is nonane, and then decane. This right over here is C9. All right, so let's talk a little bit about combustion, and what combustion actually is. It's oxidation, which means I'm adding oxygen to a reactant and then forming products that way. So this is combustion is just another term for oxidation. And the thing about hydrocarbons is they oxidize very quickly, but they oxidize very quickly after you have a particular activation energy. So if I just have a hydrocarbon sitting at room temperature, it's not necessarily going to be burned, which is good, because if you had a bucket of gasoline just sitting there, you wouldn't want it to suddenly explode on you. And the reason that is there's something called the activation energy. So you might remember this from chemistry, that if I was to draw, or just kind of sketch up maybe what the energy level of was, and so if my reactants were here and my products were down here, this would be an exothermic reaction because the products have lower energy than the reactants. But in order to get there in terms of the reaction, there's something called the activation energy, sort of a hill that I have to get over. And so you can imagine if I had a ball, it wants to go down here. It obviously has a lower energy down there, but I first got to get it up and over, and that's called the activation energy. And hydrocarbon oxidation or combustion requires this activation energy. Now, as soon as the first molecule reacts, it gives off enough energy it can get the next molecule to react, and so it's a self-perpetuating reaction. I need that first little bit of energy, and this is what comes from your spark plug. For example, in car combustion, that little spark doesn't really provide much energy, but it gets the first couple of molecules to react, so the reaction goes forward. And because of this, this is the reason why when you're dealing with hydrocarbons, for example, gasoline, you often see a sign like this that says no smoking, because you sure don't want your lit cigarette to provide that little bit of energy to go ahead and cause this reaction to begin occurring and explode on you. Now, the source of oxygen, well, the most readily source of this is the air, the atmospheric air. And so atmospheric air provides a ready amount of oxygen that you need. And so if you remember, air is more or less 21% oxygen and 79% nitrogen. And so here's, 79% nitrogen. So here's my oxygen. And this is usually a pretty good source. I mean, 21% of all the air is oxygen. But there's this nitrogen over here. And nitrogen tends not to react. We're not going to be worried about sort of NOx production here, which would be a byproduct of high temperature reactions. And so this remains more or less inert. Inert means that it doesn't react at all. And so here's my source of oxygen. And there's an important ratio. If I were to look at what 79 is over 21, the amount of nitrogen to oxygen, that number right there is 3.76. And so here's a number you're going to run into a lot in this chapter, which is the amount of nitrogen that goes with oxygen. And so since they're together, nitrogen is sort of like this little brother that kind of always tags along. I'm going to usually write my reactions such as this, where I have O2 plus 3.76 N2, recognizing that if I want to add more air, I'm always going to have to add just a proportional amount of nitrogen. And so I might put some coefficient out there. And we'll see this in a moment when we go ahead and balance chemical equations. Okay, so let's go ahead and talk about combustion reactions and balance them. And there's something called theoretical air, and another word for that is stoichiometric air. So those are synonymous terms, theoretical air and stoichiometric air. And what this is is the minimum amount of air required to form complete combustion. Well, complete combustion means I completely oxidize my hydrocarbon, and to completely oxidize my hydrocarbon means my carbon is going to go to CO2. That's completely oxidized carbon, and my water or my hydrogen is going to become H2O, which is completely oxidized hydrogen. So I went ahead and completely oxidized my hydrocarbon. So if I want to go ahead and balance this reaction for complete combustion, it's kind of straightforward because I can look and do more or less a fairly simple element balance that all the carbons on the left have to be all the carbons on the right, and so we're going to inherently have just kind of a 1 on there. That'll be our basis. So if I have a 1 in front of there, I have 2 carbons on the left. That's going to go ahead and give me 2 carbons over here on the right. I can also balance my hydrogen because it only appears in the water. I have 6 hydrogens over here. That will give me 3 waters, 3 times 2 to give me 6 waters. And now that I've determined what those 2 coefficients are, I can now balance my oxygens. And so if I see over here, I've got 2 O2s, so I have 4 oxygens, and then another 3. I have 7 oxygens, which means I'm going to have 7 halves O2, and that's going to be in front of the air component. Now notice again, I've got this in terms of parentheses because this 3.76 nitrogen is always accompanying the oxygen. So I'm not going to ever put any numbers inside there. Well, now I've only got one number left, which is I've got the nitrogens, and I have my 7 halves. I need to multiply by 3.76 to distribute it. Go ahead and get a number over here, and that would be 13.16 in front of the nitrogen. And so now I have balanced this equation with theoretical air, the minimum air, to give myself complete combustion. Now, what I could also have is something that's called excess air, and usually there's a little bit of excess air because it's hard for every single hydrocarbon molecule to find the very last oxygen molecule during a reaction. So often there'll be some excess air that we do that we might put into the system. And so in order to do that, what would end up happening is that oxygen goes through unreacted. And if I now want to balance this for excess air, so let's say we have 50% excess, which means I have half again as much air that I need. Well, I'm going to balance for stoichiometric, which would give me these numbers here. I'll rewrite them. Where I've got my 7 halves and my 13.16 over here. And then what I do if I have 50%, I'm just going to go ahead and multiply this number over here by 1.5. That's going to give me my extra 50%, which means I'm going to have a 0.5 in front of the oxygen there because I've already used up 1 with my CO2s and water. And then my nitrogen number now becomes 1.5 times 7 half times 3.76, and that number right there is 19.74. So here's my balanced reaction for excess air. Notice that I've got extra oxygen over there. I have more nitrogen coming out, so that's why this coefficient right over here is larger. And so let's look at another definition, which is known as the air-fuel ratio. And this often comes up when we describe combustion products, or combustion reactions in general. And the air-fuel ratio is defined as the mass of air over the mass of fuel. Now, the thing is that this is defined in terms of mass, but these numbers right over here, these are moles, and so I need to go ahead and convert. I want to use these numbers here to determine this ratio. I need to go ahead and convert that into mass. And the way I do that is the mass is going to become the number of moles of air times the molecular weight of air. And then the mass of fuel will be the number of moles of fuel times the molecular weight of the fuel. So let's kind of look at this reaction that we just had before and calculate our air to fuel ratio. If I look at the number of moles of air, this is my air over here. So what I have is I have 3.5 moles of oxygen, and the molecular weight of oxygen is about 32. And then I've got my 3.5 times my 3.76 for the nitrogen, times that number right there, which is going to be 28. And now I'm going to put that all over the mass of fuel, which is the number of moles of fuel. Well, that was just 1 mole of fuel. And then the molecular weight of C2H6, well, each carbon is 12, and H is 6. And so that's going to go ahead and give me a molecular weight of 30. And so if I determine my air to fuel ratio, that's about 16. I think it's about 16.02, and that's a unitless number. So that tells me I've got, in terms of mass, I've got 16 times as much air going in as I do of fuel. And that's one of the reasons why when we talk about combustion, for example, we said it was an ideal gas, even though hydrocarbons aren't ideal, is that only 1 out of 16 of those molecules in that piston cylinder was a fuel. Let me show you another way you can calculate this. Here I broke up the oxygen and the nitrogen separately, but you can also look up a molecular weight of air, which is just the mole averages of those two. And if you look it up, it's 28.84, because air is actually listed in table A1 as well, which is just going to be 21% of 32 and 79% of 28. So that would be 28.84. So I could also compute the air to fuel ratio by taking my 3.5 right there for the number of moles, and now I'm going to multiply by air. I've got 1 here and 3.76 there, so I've got 1 plus 3.76, and then its average molecular weight, which is 28.84. And that'll all be over 30 again, and that number right there is also 16.02. So you can do either one. You use your mole average molecular weight of air. Make sure you include both the 1 and the 3.76. So that number right there becomes 4.76. Let's talk about the dew point temperature. It's a pretty important number to know. So, for example, I'm still sticking with this reaction where I'm combusting ethane. And so here are my combustion products, and this is for complete combustion. And if you look, you've got 3 moles of water and 2 CO2, 13. That's actually a pretty significant amount of water in the combustion products. Now, these combustion products tend to come out hot, but then once they go through the exhaust, they tend to cool off. And so what often happens is this begins to condense. In fact, you often see this in Fairbanks when it's cold. Here on this photo here, we look at the exhaust from a car, and you can see where the water vapor is condensing out. This is not smoke. This is just water vapor condensing out. And in fact, when it's really cold in Fairbanks, this vapor comes down and then collects on the ground surface, and this is why the intersections are so icy. It's from all the combustion from the vehicles. Well, so I'd like to know what that dew point temperature is. It's also important in terms of designing, for example, heating systems, because if you have liquid forming, you have corrosion problems. So if I wanted to determine what the dew point temperature is, I need to know what the temperature at which saturation is. So remember, the partial pressure of the water over the total pressure, if it's an ideal gas mixture, and I can assume these are ideal gas mixtures here, that is proportional to the number of moles of water over the total number of moles that I have. And so if this is just my combustion products, the number of moles of water I have is simply that 3, and the total I have is all of them, 2 plus 3 plus 13.16, and so the partial pressure there is going to end up being 0.16 times atmospheric pressure, which is about 16 kPa, because atmospheric pressure is about 100 kPa. So then what I'm going to do is now look up what is Tsat at 16 kPa, and if you do that, you find that is about 55 degrees Celsius. So that means once the exhaust cools to 55 degrees Celsius, which is pretty warm, you're going to start getting condensation, and water is going to begin coming out of your exhaust products. Now I want to turn to incomplete combustion, because this is also an important topic. And there's a couple of things that can lead to incomplete combustion. So first, in this diagram here I pulled off the web, is showing complete combustion, which if you're burning hydrocarbons often gives you a nice blue flame, which means I'm giving it sufficient air. Now if I was to reduce the amount of air, so I give it less than theoretical, I would end up with insufficient oxygen to completely combust. And so often that's when you end up with sort of a yellow looking flame. You have incomplete combustion. And because it's incomplete, instead of just forming, for example, CO2 and water, what you'll end up forming is CO, which is a partially oxidized hydrocarbon, and so and some CO2 and some water. And so this is not very good. You don't want to be forming carbon monoxide. 1, you're not efficiently using your fuel, and 2, if these exhaust gases are somewhere where you can breathe, this is a very poisonous gas in fairly low concentration. You can also get other combustion products. You might end up just kind of partially oxidizing it. You might get some alcohols, for example, which is a partially oxidized hydrocarbon. But primarily what you end up running into is carbon monoxide. Now, it's not always because you didn't put enough air. Sometimes you just didn't get enough air to the fuel in time. And this often happens in cars. So here, just kind of a picture to remind you, if I have a piston inside my car, so here's my piston inside the cylinder, this combustion process is occurring, in fractions of a second. You look at how many RPMs you're running. Say you're running 5,000 RPMs. This is happening 5,000 per minute. This reaction happens in just a small fraction of a second. And so sometimes, even though there's sufficient air in there, not all the molecules will go ahead and burn. In fact, here's actually a pretty interesting picture. which is actually taken in terms of a test engine that had a glass cylinder, so they could actually look at the combustion. And what happens is you look at this, these are pictures looking straight down on the piston, as you see the combustion is occurring on the outside. This goes from 1, 2, 3, 4, the time sequence of pictures. Combustion doesn't ever happen in the middle. It starts on the walls of the cylinder because they tend to be a little bit hotter, and it works its way through, but it doesn't get to the center by the time the exhaust. So this would lead to incomplete combustion, even though there might be sufficient air in there. So two things that you can lead to incomplete combustion: not enough oxygen, or just not enough time for a reaction to occur. So the last thing I want to do is I want to look at how we would balance an incomplete combustion reaction. Well, first we have to look at what our new products are for incomplete combustion. And one of the things that we're going to end up having here is this carbon monoxide that I mentioned before. And so we might also have some oxygen, because if the reaction is happening fairly fast, we might be getting some oxygen that can react. So this is right over here would be my incomplete combustion. I can't go and balance this on the element balance quite yet because I don't know the relative amounts of CO to CO2. So if you try to balance this reaction, you find out you don't have quite enough information. Well, if you want to look at these types of analysis, what tends to happen is you go and you take a sample of gas. And so I kind of have this picture down here, and I'm saying this is a sample of my exhaust products. And so I've got my different products in there. And then you want to go ahead and just run that through an analyzer to determine the relative amounts of them. Well, first of all, if you remember the dew point, by the time you collect this and move it to the lab, this water tends to start condensing out. And so since that'll mean you change the amount of water you have, normally you just go ahead and completely dry it. So you're going to go ahead and remove all of the water molecules from it. So I'm going to remove all of these little blue ones. And then I'm going to go ahead and look at the relative amounts that I have. So here I'm going to go right up. These are all of my unknowns that I'm putting in, which is the amount of gas that I have. I remove the water from it. And then maybe I'm just going to run it through an analyzer. So here, just put up some hypothetical numbers. Let's say our analyzer said that we had 2% CO2, 0.2% carbon monoxide. I don't know how much water because we removed it. 80.2% nitrogen and 16.6 oxygen. So that's everything but not including the water. So now if I want to balance it, I could say, well, I've got a volume of gas that was large enough that I produced this many moles, which means now I don't know how many moles that I started with. So I've got an unknown amount of fuel, which I'm calling XE for XA, and then my amount of air, which is X sub A. And so what I'm going to do now is I've got three unknowns, XW, XE, and XA. These numbers were all given. My analyzer gave me what those numbers were. And I'm going to do an elemental balance, which is similar to what we were doing before, but it's nice to go through because we've got more terms here. So let's go ahead and start off, and we'll just balance our carbons. And so if I want to go ahead and balance my carbons, on the left-hand side, I've got 2 times XE, so 2 times XE, and that's the only way a carbon appears on the left. All those carbons have to go over here and appear somewhere on the right, and I've got 2 of them appearing in the carbon dioxide, and I have 0.2 of them appearing in the carbon monoxide, which is 0.2 there. So that's one of the only places the carbon has, so now I can go ahead and solve that for what the coefficient of XE is, and I'll find out that XE is equal to 1.1. Alright, so now I solved that. And now we can go ahead and do another balance. We can do a balance on all 4 of those elements that are in the reaction. I'm going to go ahead and do hydrogen. So it's on the left-hand side over here. I have 6 times XE, and I already determined what XE is, so that's now unknown. And now I'm going to look at where hydrogens appear on the right. And hydrogens appear, well, just in the XW number, so now I can find out what that is. It's 2 times XW. It's 2 because I got 2 hydrogens in terms of that. So now I can go ahead and solve for what XW is. XW is 3.3. Right, so now I've determined that value, and now I've only got one unknown left, and I can balance, well, actually I can balance either the oxygens or the nitrogens. So let's balance the oxygens, a little more interesting. So I'm going to balance my oxygens, so now I'm going to look over on the left-hand side here. I've got 2 times XA, 2 times XA, all right? And then if I look at where all of my oxygens appear on the right, I've got 2 in the CO2, so 2 times 2, because it's CO2, and then I've got 1 in the carbon monoxide there, so 0.2 in the carbon monoxide. I've got 1 in the water, so there's my XW, but I already determined that, so that's a known value there. And then I've got my oxygen down here at the end, and so I'm going to go ahead and be adding my 17.6 right in there, and that's times 2. And if I do that, I'm going to be able to now determine what the amount of air is that I have, that X sub A value. And X sub A is about 21.33. So I did that using these three balances. I can now do a nitrogen balance. In fact, you should on your own do a nitrogen balance and make sure that these numbers check out, and they should. It should go ahead and close. Otherwise, there will be something wrong in terms of the problem statement. All right, so that's how you go ahead and balance an incomplete combustion reaction. It's the same thing that you did with complete combustion. It was just, since there were so many less terms, we kind of didn't go through this methodical step in terms of balancing each one of these elements.